Hi. 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 Is it okay? So, before we go, some administrative thing first. Probably you will see the announcement already. So next Thursday, no one has class because of the congregation. So, it's university holiday. Okay, and because we need to make the class talk about our programming. So why don't we just don't meet Monday as well? So we'll skip next week. Next week no class. Then we will do the makeup class on the makeup day. I'll announce later. Is on the December 3 and 4. Then we will do our programming in the B.B.A lab. So you can come, you may not come. If you then shouldn't be a man. It's optional. The test is on December 1st. Okay, it's just 1 hour in YA. Okay, you can bring whatever you need to bring. Okay, just remember your calculator because we can't allow you to use the phone due to you know the reason, of course. So it's open book, open physical paper, but not iPad or laptop. So make sure that you also bring your set table, T table, F table, whatever table you want to bring is you'll bring your own. Okay, I'm not going to provide anything. Okay, so the other administrative thing is the assignment that have been released. Okay, so we finished today, so you basically you can consider today we give it. You have 2 weeks to do it. We cover oh no, sorry, not this one. Assignment 3 is here. Okay, it's released here, so so it should be sufficient time, I guess. If you need more time, let me know. We can extend the there, but most of them cover. We cover the sample space that we covered, sample size cover today, then we're done. Okay, and also cover. I also put the last year paper here. I'm not going to release the solution. Okay, but we'll discuss in the class in line with all the classes. Okay, so the written assignment will be given, but we'll discuss the question. Okay, so we cannot give a physical answer to that. But so I guess I should quickly review what we have done. Estimation, and then we will do hypothesis testing. Okay, so you will see hypothesis testing and estimation are so similar that there's some slight difference. Okay, later you will see. Okay, and that means that if you have a good understanding of estimation, hypothesis testing is you just need to understand what's going on. The procedure is almost the same. Okay, so that will be you will see your mind just a little bit twist a little bit, then we're done. Okay. The estimation, just to recall, what we have covered, okay, quickly, is you try to estimate what happened in the population, right? Look at the population mean, population variance. Do remind you that population mean variance are not random variable. There's number just unknown. Okay, so you have to distinguish two things. One is something you don't know. Something is random variable. Something is uncertain, right? Haven't happened yet. It's random variable. Okay, and you got the sample before you got it. You don't know which one you got. Okay, so the estimator has a way to estimate. Okay, so because you don't know what you got. Okay, and this estimator is a random variable, like the sample mean, sample variance, all this kind of stuff. Okay, it depends on what you actually got. Okay, and estimates what actually you got is a number. Okay, so that has to be this. You have to distinguish the difference between the two, and there are two different kinds of estimator. One is a point, one is interval, right? Point is exactly pinpoint a number that represents your guess. Okay, this is your guess, single guess. And interval estimate is multiple guess, right? You guess not just a number, but interval number. Okay. And remind you what are the difference is, suppose you are looking at analysts and they tell you what is the Hang Seng index today, give you the one number, that's point estimate. It gives you it's a range, right? From say 16,000 to 17,000, then it will be interval. And after that, we learn some property of point estimator, right? And biasness, efficient, and consistent. Which quickly is just say unbiased means if you do many sample, okay, and each sample according to estimator, right? You have different estimate, and average of these estimates, okay, is actually uncover what we want to guess. Okay, so do note that this is hypothetical, right? Because we actually just do one sample, but the idea is, imagine that we repeat this many times, then we have many estimates, then average of those is get what we want. And efficiency means given that they are unbiased, okay, they on average is a target. If they are closer to the target, it's better, right? That means they're closer. Okay, accuracy of a hit, they're closer. And consistency is a little bit more generic, right? It's saying that if I have a larger and larger sample, okay, and my guess would be so close to it, okay, and it's so close that actually there's no more probability anymore, right? It's close to it that the probability that it deviates from what it is basically zero, right? Or you can say less than this one, right? The same thing. Okay. And we say sample mean satisfy all those nice property. And for sample variance, you need to take -1 in order to be unbiased. So that is what we cover. Okay. And sample proportion, when you have binary data, sample mean the sample proportion. So that is a nice property that inherit from the sample mean. And when we have binary data, okay, and do note that we don't use n, we don't divide by n-1. Okay? There are some reason that we use this, okay, and although it's biased, but it's still consistent, and the bias would go away when n is big. So, and also we usually have big n for binary data, so it's not that you don't need to worry too much about that. Okay, and we still keep using this. Okay, and the last thing we cover is interval estimate. So I will go a little bit slower because I think the way to do calculation, I need to review a little bit because we will do the same, almost the same calculation today. We're going to hypothesis testing. So I want to make sure that everyone is on the same page. Okay. So the idea of this is instead of estimate one point, you want to estimate a bunch of points, a range, and we want that there's a high probability that your range, say the sample mean, right, left and right go down a range, will include the true mean. Okay, let me repeat the statement, right? We know X bar is good, right? We want X bar go left and right, that constitute a range, right? Or interval, right? We go X bar, go right by M, and go left by M, right? Because it's the center is X bar, right? Such that we have a high probability, alpha is very small, right? A very small alpha, such that that will be included. Is that clear what we're doing? Okay. Let me repeat the statement, it's very important, so I repeat once again. What we want is I have point estimate, okay, for the population mean, right? That's the only thing we care, population mean, okay? We use the sample mean X bar to estimate. That is have a very nice property we discussed, okay? But we want more, right? We want more. We want that. We want to have we extend it left by M, right by M for X bar, okay? We extend left and right by M such that, okay, whenever I construct a sample mean, I go left by M, right by M. In the case that I construct this, I have very high probability it will include the mu. Okay. Or remember, mu is unknown. I don't know where, but I want it to be able to include the mu with high probability. Okay. And it can be shown, which we don't want to repeat again. This M, okay, actually is two parts. Okay. The first part depends on the bell, right? The bell thing. And it depends on bell in the sense that depend on how likely you want to include it, right? If you want alpha, right, it's with the probability that you just outside it, right? You want it to be smaller, then this will be bigger, right? Because this, remember, Z alpha 2 is what? Just draw a graph here, right? Right? That the notation here set alpha 2 is the following. Here I have a 0 here, okay? I have left and right, okay? Here alpha over 2, okay? That's what it means, okay? But by symmetry, right? This is C alpha 2, right? And this is Z, this is alpha 2, right? And this is alpha over 2, okay? And that means this is 1 minus alpha. So this is how you connect, right? So that's Z alpha 2 actually means the right tail area, right? This is exactly opposite the way we do the big F, right? Big F is the left area, okay? And usually we denote this X, Z lower subscript is the right tail area, okay? And you ask me why they do it, I don't know. This is the book they do it. I mean, your mind actually has the twist, okay? I don't know why, but don't ask me, okay? This is the book the book they do it, okay? Don't ask me why I got crazy, but right? But of course, if you want, this is exactly, if you don't like this notation, everybody uses just this, right? 1 minus, right? If you don't do that, right? That's this. Not exactly this guy, but math is like this. It's the inverse, f of the inverse, because not exactly f, right? F is asking, you give number, I give the probability, right? It's inverse. You give a probability, I give the number, right? So, but I don't want to go to too much math here, but that is what the inverse of the tail area. Okay, because asking you this area, right? 1 minus alpha 2, and this is the number there. Okay. And that is the slide that you should remember. Okay. And this is the slide that you will be using all the time. Okay. Is the, you have the sample mean. Okay. Suppose you know the sigma, you just go by this. Okay. Let me go to example again, because as I said, this is the, I guess one of the most important example that you should know how to handle. Okay. So I have a population standard deviation is 4. Okay. Don't ask me how we get this. There's some way to get it, but we just assume we know it. Okay. And n is 64 and x bar is 3. To remind you that x bar is the point estimate. So if you want to go interval estimate, it's this, right? This is the formula. If you just check your handout, like this, right? And let's check each one. This one you know, which is 3, right? And sigma is here, right? And n 64 is here, orange, right? And this guy, right? It just norm as inward, right? I want 95, right? Which means that 0.95 here, right? And the other both side is 0.025, right? And that means that this is 0.975, right? So if we input to Excel, this is the one, right? Or you look at the Z table, look at the entry where it's 0.975, and that's it, right? So that's how we do. Is that okay? Let me know if you have any issue, because today we will do this again. Very similar, okay? Just want to make sure that everyone knows what's going on, okay? Okay, I'll go to the next slide. So some of you asked interpretation of this. It's just very simple. Imagine that you have the problem is, okay, we said the interval has high probability include the mu. Okay, that's a correct interpretation. Okay, but the problem is once we collect the data, right, there's no more probability, right? Then how can we describe this, right? So that actually you can see we don't call probability interval, right? We call confidence interval. The reason is there's no more probability once you collect data. Okay. So then how will you interpret how do you call it, why you call it confidence? It means that suppose I have collect 100 sample. Okay. I don't do it, just do one, but suppose I collect 100 of them. Okay. And then I can construct 100 confidence interval. Right? Like this, right? Have sample mean, go left and right, right? And afterward, what we know is if I have construct 100 of them, I know 95 of them will include the true mean, although I don't know which one. Okay, but 95 of them will include. And the confidence means that I have a confidence of this process that it might include or not, but we don't know. Okay, but there's no probability. Okay, because we cannot even say probability, right? Because probability is something that we haven't happened, right? If it happens, there's no more probability, right? Whether it is or it is not, we just don't know. Is that okay? So that's the interpretation. I mean, it's important when you go to statistics class, right? But I'm not going to trick you in your assignment or in your exam how to interpret those. But that is very important in other class that they would be distinguished whether you know it. But I already give you the interpretation, okay? So shouldn't be a problem, okay? But do remind you that before you do the sample, it's probability, right? But once you do it, you no longer call it probability, right? Because no probability anymore. That's why we distinguish what estimate or estimator. The estimator have 95% probability include the mu, right? But the estimate, no probability. You can only say 95% confidence, right? That include the mean. Okay, it's not probability. Basically, we invent a term to say probability, but it's not probability. Okay, so that is more or less like that. I hope answer you the question, kind of. So next is if I don't know sigma, right? You replace it by S, right? Use Tn minus 1. Okay. So that is the situation, right? Let me go to example again, because I think it's important. We call this today again, right? So just make sure that we know. So the only difference from this is I don't know the population variance. So the formula we use is this guy, right? Okay. And all of them are pretty natural. This one is the one that we just got the sample, right? The only thing is this guy, okay? Tn minus 1. It should be Tn minus 1 alpha over 2, right? So I have 95, right? And there will be no different as you expect, right? This is 0.975, right? Because the middle is 95, right? And both sides 5%, right? And up to the boundary is 0.975. Okay. The only thing to worry about is this n minus 1, right? So you would use in Excel just T inward for 975 and 19. Okay. That would be the right, because from probability to a number here is the inverse. Right? So that would be the table that you would do. Okay. Is that okay? So now we talk about sample proportion, okay? And there's a one remarkable difference is, even though we don't know the sample mean, population variance, we don't need to use T, okay? We will use Z and replace this P. So because P times P is a good estimation of sigma. So that is the reason why we do this approximation. But you have to remind one of the things why this is fine is because for Z, well, for this binary data, you should N is big, right? Actually, use T has not much different anyway, right? Because you look at the T table, you can try to look at it when T is more than 100 or above. Actually, more than 120 is almost like no different from Z. Maybe only different from 3 or 4 decimal places, right? For most of the purpose, right? You don't have to worry about those. Okay, so that's why in all the textbook, use this one, right? So this is the formula for the proportion. Okay, let's work it out, and then you will see how we do that. Okay, so the sample proportion and sample size here. I don't need to know anything, right? I want to guess what is the population proportion, right? And I want 95% interval, right? So the formula is very simple. It's just P plus minus Z R over 2, right? P1 minus P over N, right? So this is the formula, right? And you know the P is 0.025, N is 64, and this is 1.96, right? Already you know, right? So of course, in most practicality, you may use 1.96, but you can see, I mean, by rule of thumb, actually, if you use 2, that would be mostly fine as a rule of thumb, right? So if you, as a first guess, if you're unable to get anything, computer in your hand, no calculator, right? Then you can just plus minus 2 of the standard deviation, right? So that would be easiest thing to do, right? But if you calculate that, that's very simple. Okay. I guess I don't need to tell you how to plug in the number, right? Just that. Okay, sample size. Okay, so this part actually tell you how you design your survey. Okay, we just touch a little bit on the fact that, okay, we talk about data collection. This only time we talk about how much data you're going to collect, right? And before we just give it to you, right? But we now tell you how many N you want to go, right? Suppose you do a survey for your project. I mean, probably not now, maybe some of you doing it, right? You consider beforehand how many survey you need to get, right? How many questionnaire you have to print out, right? It's an important question, right? So, so that is very simple, okay? And how many sample is like we want to do estimation, right? We want to estimate mu, right? And the question is how we want to do interval estimate, and we want to have the precision, which is the margin of error, right? Where sample mean to go left and right, right? If the margin of error is very small, that's very desirable, right? Because we control the margin of error, right? We want our desirable margin of error, okay? So this is margin of error. right? And if you use the high school math, make n the subject, right? So multiple square root n on both sides, right? And this m you go down, and square on both sides, right? Because put n, you get this answer, okay? And probably you would wonder why I have the ceiling function, right? Because I want to be integer, right? So if I have 14.5, I have 16, but for 15, right? I have 16.1, I have 17. Just a smallest integer that bigger than or equal to this number. Okay. So you tell me how accurate you want, maybe 0.1, right? Accurate up to 1 decimal places, right? Or up to margin of error is 1 or 2 or 3 or 0.1, 0.2, 0.3. How would like the answer to be, right? Because you want the answer to be up to how many decimal places, right? What is the margin of error you allow, right? Because we don't know where the sample mean is, right? But we just look at it, how good is your data, right? Let's see the example, then you will see what I'm saying. So this example is very simple, okay? And for some reason, we know the standard deviation of 10, okay? And this standard deviation, actually you can consider the upper bound of standard deviation is from the range, right? The standard deviation cannot be bigger than the range of the data set, right? Suppose you consider IQ, right? And most is 100, and most is like maybe 50 to maybe from 80 to 120, right? The range, the standard deviation maybe just 10, right? Usually you have some idea how to estimate, okay? Maybe half of the range or whatever, okay? But just say we know from historical data or some idea that's around 10. What we want is, okay, we have to guess how many samples to collect, such that once we collect with a sample mean, right, and we go left and right according to our formula, right? Because the formula is, suppose we get our sample mean, right? We go left and right, this formula like this, right? Right? We don't know this guy because we don't do the sample, but we want to make sure the margin of error, okay? How much left and right to go? It's no more than 4. That's I tell what we want, right? This your decision. Why is within 4? You can within 2, within 3, depending on your purpose, right? Because you will see the smaller the margin of error, you have more sample. Then you decide what it is, right? Before we do it. Okay? And I construct 95% interval, you know it's 1.96. We've done so much, we don't need to repeat it, right? I want this, once we're done, I want this at most 4. Right? So then I just plug in the formula, right? And I calculate if I want margin of error is 4, understand the deviation is 10, then I need 25 observation, right? Of course, you can see if I make it 2, right? Then I need 100, right? So it really depends on how small the margin of error you want. Yes. Yeah, because you want to make sure it's less than 4, right? 24 is not sufficient to get 4, right? So you make it the smallest integer that's sufficient or larger than that one. If 24.000, then it's the 24, right? Of course, I mean, in reality, you get 24 or 25 actually not make a difference, right? But in our convention, we just make the smallest one, right? But in the reality, right? In reality, there's no difference anyway. We can imagine, right? Add 1 or subtract 1 has no, I mean, no one actually care, but just for our class, we have to be specific, right? What to pick. Is that okay? And this is the convention not invented by me, or the book does this. Okay. So what I taught in this class is nothing new, it's everything everyone knows. I mean, even you study whatever section, what I do is the difference between I and other teacher is possibly how to interpret, how to tell you the story. Okay, everyone give the same formula. Okay, you go to other class, the same formula, the textbook, the same story, but it's the way we present. Is that okay? So the idea, just to remind you why we do this, is we want to, before you do a survey, you want to figure out, given all this margin of error, then you know what to predict, right? Because you already know. Okay, is that clear? Okay, and if you ask me how to come up with 10, there are many ways to come up with 10, right? But you would tend to give up about overestimate this population variance, right? Then you only oversample, that's no problem. Is that okay? Because remember, if you assume normal bell curve, right? 99% is within 3 SD, right? If you know the range of the data, right, divided by 6, then it's the SD, right? Suppose I right, you remember IQ, right? Why I say statistical 10 is good one? Because IQ usually is range from 70 to 130, right? The 6 SD is the range. That's the easiest way to guess, right? If you believe bell curve cover 99%, then this is a good estimate already. So that's why I get a 10 here, right? Suppose you want to get the margin of error, the average IQ is within 4, right? Go up by 4, less by 4. That's the thing you get is sufficient for your purpose. Okay, then you want to be there. Is that clear? So you can imagine the sample proportion. Okay, if I have good guess of pi, okay, right, then the formula is the same. Okay, so remember pi is like I have some idea that how many female students in CHK, maybe 0.7, 0.3, right? But I want to check it, right? I just put this, right? Remember, this pi are your guess. Okay, not exactly the pi, but you think that it fit, right? So the example like this, right? Right. Suppose from history, you think that it's like 0.4, right? Maybe how many boys in CHK, right? And then you want to calculate, you want to collect data, right? And you estimate pi times 1 pi and put in the formula there, right? And you're done, right? Because remember the formula, right? It's like this, right? Z over 2 square pi 1 minus pi 1 minus pi, right? Over ME square, right? So just put things you want to put in and calculate 92 point something minus 3. Okay, so that would be the way you would go forward. Okay, there's nothing special here, just the formula plug in and then you're done, right? And the reason I think is very simple already, right? Because you understand that's basically looking at the confidence interval estimator a different way, right? So now, what I want is to tell you the very last one, okay? That requires a little bit math, little bit, very little math, okay? The very little math is not too realistic that I know the pi, okay? If I know the pi, what I'm doing, why I need to do estimation, right? If I could estimate, right? Of course, I want to still do it anyway. But in most cases, I don't know, right? Or I don't even have a good estimate because it's easy IQ, right? You know the minimum, maximum is a reasonable range. That's no problem, right? But how many? If I go to a random, say, a random high school, how many boys and girls? I don't have a good clue, right? Maybe 0.5, maybe 0.6. I really don't know. So how are you going to solve this problem? We'll use the math that for pi times minus pi, where pi is between 0 to 1, the maximum is 1/4. Why? Look at the graph. This is simple math here. You can draw a diagram. This is a parabola, right? Pi times minus pi. When pi is 0, this is 0, right? When pi is 1, this is also 0, right? Pi times 1 of pi, right? And you can easily show if you learn math is parabola, right? When actually in the middle, 1/2 times 1/2 is 1/4. That's highest. Okay? And that is contrasted equation. If you still remember your high school math, okay? It doesn't matter. We don't need to use the high school math anyway. You just need to know this is this shape. The maximum is 1/4 for pi times 1 pi, and that's what we need, right? Because I don't need to guess what it is. I just pick the largest one value, and that's done. Okay, because the largest variance for a binomial variable is 1/4. Right? I think we talk about this when we talk about binomial random variable. Okay, just replace it by 1/4. So that's the formula there, right? You can see what I do is, I don't know, I replace it by 1/4. Okay, so that's the only thing I do. Okay, that's the only thing I do. I don't know, I just discard. This is the formula. And remember, the formula is this, right? Just write down, right? Z alpha over 2 square pi 1 minus pi me square, right? And that's Z and me square, right? We know very well. This pi times minus pi is replaced by 1/4, and that's it. Okay, and you look at this question. Okay, look at this question. I have to point out several things that actually what you observe in the real world is look like this. Very often when there's an election in the US or many places in the world, you will see that they ask for sometimes like 100 people, right? And sometimes they look for 1,000 people, right? Or most often is 1,000 people is sufficient, right? You may ask why, right? They look at 95%, right? And you can easily check, right? If it is within, I think, 0.05, then it's just like 1,000. Okay, and it depends on how big your number want to be, right? It's 10%, it's 1%, 10%, right? If you want 0.01, okay, then it's like 10,000, right? 100, yeah, it's like 10,000. Is that clear? So that is the reason why, even though the US is very big, right? It doesn't mean that you need more people, right? And you will surprised to see in the news, no matter which country, looking at the survey for election, US or UK or Germany or whatever, the sample size they use is the same or very similar, 1,000, 2,000 or 3,000, right? It is because you just ask for this, right? As long as you want the accuracy the same, it doesn't really matter what the underlying the population N is, right? Doesn't matter how many people in the US, how many people in Germany, how many people in Canada, right? Even though you do it in China, 1.4 billion, you just need 10,000 or 100,000 is sufficient. You don't need to ask 1 million people, even though China is very big, right? Depend on the precision. Okay, that's different from other cases, right? where you have more sample, you have more problem, but this one, you don't need to worry about. Okay, this one also highlight. Is that okay? So Excel, I don't have anything to say because Excel, this function is not very useful, just a way to handle to calculate the interval easily. So I just want to skip that part because it just make it faster. There's no you already know all the calculations, so I don't want to spend time on that. Okay. So we're done with estimation. Okay. So before, is that okay? So before I have a break, I want to describe the meaning of hypothesis testing and estimation very quickly. Just 1 minute. This is not fast, don't worry. I will not take away the time from the break. Just very quickly. Okay. So let me clean this up because it's very simple idea. And you see all the procedure is very similar. Okay. The reason is being hypothesis testing. Okay. So the idea is that one way to think about hypothesis testing is say like this. Okay. This drink is at 250 ml. Okay, I think everyone knows it. Let me drink this here. Then you want to, say, suppose you are working for Consumer Council, right? You want to make sure that it's no less than 250, right? So what are you going to do to see whether they're telling lie or not, right? Is to buy one and measure, right? If it's above 250, then you don't have anything to say. If below, then you say, okay, that's a problem, right? But the guy with the shop will say, okay, no, I mean, although I'm just a little bit below, but can be just some problem with the machine, it happened to be, right? And if they said, on average, I'm correct, that's no problem. I mean, just a little bit lower. So, and so for how can Consumer Council conclude that the seller is not telling the truth? Okay, same as auditor, you can do the same thing idea, right? The idea is you collect data, look at the sample mean, construct the confidence interval. If the interval doesn't include 250, then you think that you're not going to believe the guy. That's it. Let me repeat the statement. Someone claimed this is 250. Okay. So how can you say whether the claim is supported by data or not? You just do the sample mean and do the CI we have done. If CI include 250, yeah, I don't have enough evidence to not to support what you say, but my interval doesn't include 250, then no, I can't, the data don't support what you said. That's what it is. Okay. Is that clear? So you can imagine that you apply to your audit, right? Some you audit the same idea, right? Someone claim in the warehouse, right? And this is what they said, and then you actually get that data and do the sampling, and then doesn't include what they said, then you cannot attest to what the client told you. Okay, so let's a break of 15 minutes, and then we'll come back. As you can see, it's very similar, so don't worry. It's very simple as we can measure. Let me open the U reply so that you can you will reply to me, right? That's what the U reply means. And as the same, I will go around to see if you have a question. So feel free to fill in so that you can let me know which part I should explain more or less, or I'm too fast, too slow. Okay. Just to remind you that next week we don't have class because that is rescheduled to the makeup week. We cover optional material for R&R Studio. You don't pay attention to that. So let's see how things go. Oh, yeah, that's good. I think it's very tired, everyone, because presentation and assignment and almost at the end of semester. So I hope next week you have a break. So I have here. There's no class next week. Just make sure that you know. So we make up after at the end of semester. Hopefully, you may or you may not attend. It's also okay, optional. This is bitter. No, this is good. It's low sugar, so it's not bitter. It's very tasty. No, that's good. Oh, so someone must be sleeping. Today is not Monday. Today is Thursday. So make sure that you don't make a mistake. Yeah, I think today is sunny. Yeah. Oh, the key point is sleeping. Yeah. Well, I suppose Z is mean the bell curve. Okay. Standard normal is Z. So that's why you feel sleepy. Oh, now I get it. Why you get sleepy? Because I always thought about Z. Okay. That makes sense. The margin error. Yeah, exactly. So everyone get some kind of the. So I think now I'm at a good speed. Okay, not too bad. I mean, so don't worry. I think we already passed the most difficult part already, because the hypothesis testing is almost the same as estimation, the idea. And what the remaining is difficult part is ANOVA and regression. But you will see it's not very complicated. Okay, so the most difficult part is already there. It's already almost done. Oh, you still got midterm? Yeah, I really hate midterm, so that's why I never put midterm when I have to teach. So since I become teacher, I never give midterm. So hope you don't feel. Oh yeah. So don't worry about that. One thing is you get older, you don't feel that tired. You can see probably some of you observe your grandpa and grandma don't need to sleep. Need to sleep only 3 to 4 hours, 5 hours. The older you get, you sleep less. So I sleep less than when I was young. You guys sleep more because you guys are growing. After you get to 25, 26, 27, 28, then you can sleep less and less and less. So don't worry about it. You sleep more now, that's okay. So it's okay. So don't worry about that. Ha 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 ha. Okay. I understand it's very sleepy. Hope that you get better after 1 week of rest from this class. Okay. So hypothesis testing. So as I have already hinted, what we are doing is we are testing hypothesis. Okay, that means that there is some claim, okay, by a client, by a boss, by somebody. Okay, we want to use the data to see if the evidence from the data supporting the claim. Okay, actually for those who do accounting, that is actually what it's doing, right? Looking at the data, evidence, support or not. Okay, and this also in the court as well, right? The court, you would assume to be innocent, right? And there will be evidence presented in the court, and then the judge or the jury will decide whether you are guilty or not, right? So there are two parts of this topic. The first one is called one sample. One sample will be almost like the lemon tea story we said today. Okay, and two sample will be very similar as well. Okay, there will be little complication in the formula, but the idea will be exactly the same. Okay, just you consider whether what is being claimed is within the common interval estimate. Very similar. Okay, of course, although what we cover is the thing we cover is very simple, very easy, but if you go further, it can be very difficult. Okay? But what we cover is operational stuff, so it's not something complicated. So it's called one sample. Okay? So the overreach idea of hypothesis testing is you want to see the claim, some statement about the population. Basically, this claim is population statement, right? We want to say whether the population mean is equal to some number, right? That's a big claim. Okay, we want to see if this is correct. Okay, and the way we do is like the court system. We will assume the defendant are innocent until proven, right? Without reasonable doubt. Okay, so the same is we assume the claim is correct. Okay, and then we'll maintain it unless there's sufficient evidence to reject it. Okay, that means that high probability that's wrong, right? So here we have some terminology. Okay, it's called null hypothesis alternative. Null is the one that we keep it unless there's a data say no. Okay, null is like innocent, right? Alternative is guilty, right? You will remain null until you proven guilty. Okay, and how you get null, how you get alternative. In the court, it's very simple, right? Always innocent until guilty. This is the British system, right? In the mainland, is opposite, right? You are assumed to be guilty, and you have to prove you're innocent. If my understanding of law is correct, okay, the system is a little bit different, right? Which one is better or which, I don't know, but at least the different way to think about the problem. Okay, so in statistics application, how you determine the null. Okay, null is, there are two ways to determine the null. Null is based on what actually you have right now, it's null, right? Or you want to, things you want to reject is a null, right? This is 250, right? ml, this is null. You want to reject it. Okay, it's alternative. And it's called X1 or X8, depending on the book you're reading. X null is X0 is X0. So depend on the book they call it. Okay. What is hypothesis testing? Okay. Hypothesis testing is just trying to say, before we do the sample, we need to tell us, okay, what kind of value we want to reject the null, what kind then we don't. Okay. So that is definition, right? Suppose at 250, right? And one of the obvious rejection region will be, suppose that if what the sample you got is always empty, it's always 0, right? Then of course it's cheating, right? And this is extreme case, right? If every time what you get is more than 250, then you never reject, right? It's acceptance region, right? But the problem is intermediate, how you make decision. Okay, will be very clear very soon. So we distinguish the two things. One is called simple hypothesis. The other is called composite. Okay, the difference is very simple. Simple is trying to say population mean is 3, okay, or 4 or 5, just one number. If it's not one number, that's called composite. Okay, one number, simple. Not one number, composite. Okay, basically just very similar to point estimate. The simple one. That's one point. Okay, for our class, actually for all introductory class that you learn, or even for advanced class, what you do is just the null is always simple. We just claim that like this, right? We claim this t is 250. That's it. It's one number. Okay. And then the alternative is always composite. Okay? And you ask what happened if I reverse it, things are very different. We only able to teach you this one because beyond that is way beyond our class. Okay. So the alternative that you learn usually consists of 2 different styles. One style is called one-sided the other is two-sided. Okay, and I will tell you when to use which. Okay, and when you use less than, when you more than, when not equal to. Very simple. Consider your consumer council. You want to test this. The volume is no less than 250, right? So that means that if I would not very happy, I will jump up if it is less than 250, right? So that tells us the rejection region, right? So if I want it, I would not be very happy when it's less than 250. This is what you adopt. Okay. When you want to adopt more than, is imagine that now it's very common. The news, Japanese food, they talk about the Japanese seafood has a radioactive element there, right? If it's more than a certain level, then the government will jump up, right? So you will not be happy if more than. Okay, that's a problem. And last one will be why you use two-sided. Okay, as auditor, right? You try to do audit, right? You want to attest to the statement claimed by the client have to be accurate, right? The material misstatement comes from whether it's exactly equal to what they said, right? Is it sufficiently equal, right? If more than, you're not happy. Less than, you're not happy as well, right? Of course, so some case you're just not happy with more than, less than, but in most cases for auditing, right, you have to be precise, right? It should be, right? You will not be happy it's too much, it will not be too little, then you'll be two-sided, okay? When to use which, again, is whether when you want to draw the conclusion, right? Is that clear? So as I said, when use more than less than, this is the idea. Okay. So example like this, why is one-sided? Okay. Consider you are a owner of a local club, okay, and you want to see whether it's agent society, right? You want to see whether the median age is more than 45 or less than 45, right? If too old, then probably you need to change, right? You cannot do K-pop or what, right? You have to use more old style stuff, right? Maybe TVB drama or whatever, right? Old style stuff, right? And the now is always, as I said, it's always simple. The alternative is more than, right? More than, you do something. If too little, you don't do anything, right? You will take action if more than. So that's more than. Is that clear? The reason is you only want to take action. If the age is more than 45, then you would try to change, right? Because your club is already a lot of K-pop or J-pop or whatever new stuff, right? And now you're thinking agent society, right? All the young people go to Shenzhen to consume, right? What left is the old people, right? So do you need to put back the TVB show, right? And that's a problem. Is that clear? You're not confused, is it? Can I help you? Is it okay? Hi. Why is H now is equal? In our class, we always do equal. Okay, in this particular case, in some textbook, they will use less than or equal to. Okay, but that is for notation because we always use this guy when we do testing. So in our class, we always use equal. Okay, whenever equal to less than, actually has no difference. Some book you will see that, but technically speaking, actually you're doing that anyway. Okay, we have maintained ourselves. This now is always simple. Okay, Alternative is we don't know which side, so I'll give an example like this. So a firm had to claim that their mean daily revenue is 3,000, right? And as an auditor, you want to decide whether the claim is true, right? If it's more than, way more than 3,000 or way less, then actually it's not very good, right? Understatement or overstatement is a misstatement, right? So you want to make sure that it is equal to or not equal to, right? It's not one-sided, it's both sides, right? Both sides, you would not be very happy. Is that okay? Do you have any question? So it's very conceptual, but because the procedure is very simple, because I already told you already, so it's not something complicated. So now we come to the idea of test statistics, okay? And the statistics, okay, will define what do you think is rejection region or acceptance, which I will be more precise, okay? But there will be what we call the critical value, okay? And later you will see that actually the 1.96 or negative 1.96 is the thing. Okay, later you will see, but a test statistic is actually based on the sample, okay? We will tell you the value of the statistics, and then you will tell me that you're going to reject or not, okay? You later see they are actually the Z and the T, okay? Very clear, will be very clear very soon. Okay, that's definition of test statistics, okay? It's just like statistics, but it will be tell you the region, okay? Basically, it's like we say related to sample mean, okay? Sample mean, but normalized sample mean. Okay, later you will see, okay? But I will be more clear soon. Okay, don't worry about that. Okay. And one idea is like this, okay? If I have the alternative X1, okay, is say mu bigger than A, you have a problem, right? It's like how much harmful material or how much bigger, say, like in this tea, right? It said low sugar, right? If a lot of sugar, then the government will come in and say this is not low sugar, right? So that means that if the sample mean is large enough, then you want to think X1 is more likely than X0, right? So that's a rejection region. Okay. And look at the volume is 250, right? If my X1 is less than enough small number, then I will just reject. Okay. And if my X1 is not equal to, that means that if my sample mean is too large or sample mean is too small, then I will not be very happy. Okay, so it's still very kind of like abstract, but I give you example soon. Okay, after I talk about 2 to 3 more slides, then I'll talk about the more concrete. So far we talk about things that is not rely on sample mean, right? But later we focus on sample mean only. Okay, at the very end of this topic, we talk about population variance, but we will talk about most of the case. We'll talk about sample mean only. Okay. So here we talk about one technical definition, what we call statistical error. Okay. If we do decision based on statistics or based on probability, we never sure that we do a right decision, right? Unless we collect all the data in the world. After that, then we know everything, then we never make mistake, right? Because when we make decision, it always based on the data. And the data is probabilistically realized, right? Just imagine you're a doctor, right? You do many tests, right? and you're still not sure the patient is actually get the disease or not, right? Because you're not living inside the patient. Okay, and then in that case, you have to try to, based on the test result, medical test result, try to give treatment, right? And it can be correct or wrong, right? And you don't know that guy actually have disease. I remember during the pandemic, right? You do the ART test, right? And there's I don't know, there's several tests you can do, right, to see whether you're COVID, right? And the two type of error, right? If the now X0 is suppose you don't have the disease, right? X now is you don't have disease, right? But you don't have disease, but you actually say you have disease, right? Then it's an error, right? And type 2 is you have disease, but you don't really say it, right? The X now is false, but you are failed to reject. It's called type 2 error. Okay, and usually they thought type 1 error is called the false negative, right? And type 2 error is false positive. Okay, but anyway, I don't use this terminology because it's very complicated. Okay, if you don't reject you reject the wrong, now it's type 1 error, and you fail to reject type 2. But why this is alpha? Later you will see is actually correlated to the confidence interval. We have 1 minus alpha. This the same alpha there. Okay, so that is the model. I mean, very technical still. Okay, this last technical slide is if true, you reject is type 1. False, you don't reject is beta. Okay, and the other two are correct, right? And probably the question you may imagine that can I reduce both? Okay, the problem is alpha and beta trade-off. The bigger the alpha, the smaller the beta. Okay, you reduce the beta, you increase alpha. You reduce alpha, you have increased beta. Later you will see clearly what I'm saying. I've given a more concrete example, but the only way that you can reduce both is to increase sample size. Okay, more sample, reduce both. Okay, enough terminology. Give example now. Okay, I think the last terminology here. Okay, it's called p-value. Okay, p-value is defined as the smallest level that we will reject action now. Okay, and now it's a little bit complicated. I will give example, then you will see what happens. Later we can come back to this definition because I think now it's very complicated to understand without going into detail. Okay, so let me give you the framework for you to do hypothesis testing. Always this 3 standard. Okay, first one, you tell me what you want to do, right? Simple hypothesis and alternative. Okay, and based on what we know, we use Z, T, or F. Okay, for sample mean is Z or T, right? And F will be the variance. Later you will talk about that. And you tell me what is alpha. Okay, remember alpha is the the level that you would conduct the type 1 error. Type 1 error is the fact that X now is true, you reject it. Okay, you reject the wrong now. Okay, you want to take action, but you reject it. Alpha, of course, is as small as you want, usually 5% or 1%. Okay, but do remember the smaller alpha you choose, the bigger the beta is. Okay, there's no free lunch. Okay, and historically is the alpha. Okay, and once you pick the alpha, okay, you would do the test statistic or the p-value method. I will elaborate later. Okay, I will elaborate now, so don't worry. So far, bunch of stuff. You probably overwhelmed by the thing. Don't worry. I will illustrate the procedure. They illustrate everything there. Okay, then you will see we follow this procedure all the time. So don't worry about that. So let's give a concrete example of how we do that. Okay. So under central limit theorem or normality, we know the sample mean for this guy. So remember, we have this all the time. Okay. And the question is, if I know sigma square is a Z test, I don't know the T test. Okay. But today we focus on Z test only. Okay. After we come back, so 2 weeks later, we'll talk about T. Okay. So this is the procedure. Okay. It's exactly what I said before the break. I want to prove this drink has 250. That's A. Okay. I want the volume of the drink is 50. Okay. And I collect data. Okay. If this is true, okay, remember what we do is hypothesizing is assume X0 is true. Okay. Assume that's true. The sample mean you got, okay, will be a bell curve, goes around 250, right? We know the sigma and depend on n, right? This is what we get, right? So remember, it's the following, right? The idea is the following. It's very simple. I draw a graph, then you understand. So what I have is here, right? And 250 is here. Okay, it's a bell. Okay. And we know sigma square, right? And the sigma square n is the variance, right? The bell curve, we know the mean, we know the variance. Variance depends on the sample size you got, right? The larger the n, the more narrow the bell, right? It depends on the sample size. Okay. Now, the question would be this. Okay. We need to specify, okay, when you want to accept or reject this. Okay. And it really depends on your H1. Okay, take it down H1. What H1? Okay. And let me scheme what I'm doing. Okay. What I do is a right tail. Okay. So my H1 is like this. Mu is more than 250. Right? This X1, X0 is mu is 250. Okay. The thing I want to do is the following, right? If it's more than 250 a lot, then I will not be very happy, right? Because what I get is, right, for this, right? If more than 250, right, I'm not very happy, right? Because maybe you are the owner of the firm, you don't want to be too much more than 250, right? 250 is a good one. You're the quality control, right? More than that, you actually lose money, right? So if it's here, there you don't have anything to say, right? You don't have any problem, right? More than 250, there's a problem. But how much? If 251, are you going to say something? 252, are you going to say something? Probably what we want is, okay, the distance between this and 250 is large enough, right? If it's so far from 250, then you want to say more than 250, then equal to 250, right? Because that's what you do through the data to decide which one is going to be, right? But how much is big enough to say it's away from 250? How big enough? We use probability, right? We want to say the area on the right-hand side, based on this one, the area on the right-hand side is small. This is small. And how small it is alpha. Or alpha over 2 depends on the alpha. Okay? It's alpha area. Okay. Do note that this alpha is exactly the type 1 error. Type error is, even though it's true, right? There's probability end up here, right? So by designing, we set up what is my alpha. We already decided how to test this, right? Of course, if I set smaller alpha, I will have a bigger beta. Okay. The reason that is because of I have smaller alpha, right? And this is very difficult to reject, right? And but that means that I would able to commit more other error, beta error. Beta error is even though it's wrong, I can't really reject it, right? Because if the real one is 255, 251 or 250.1, I can't really reject it, right? Because I make it so, this is so small, right? Even though it's wrong, then I can't really reject it. But anyway, I'm not going to that far. You just need to know, okay? The alpha is redesigned, okay? We make this very small, and we tell us what is this number, right? And you can see there's no different from hypothesis, sorry, interval estimation, right? Interval estimation is actually, you know what this number is, right? In this right tail, okay? If you do have interval estimate or the same idea, this guy is 250 plus Z alpha over 2, Z alpha and over N. Okay. Do note that it's not alpha over 2, it's alpha, right? The reason is because alpha is here, right? The tail is alpha. Okay. So in this case, actually, you reject if, okay, depending on the sample size you got, right? If you get is more than this number, okay, then you would say it's more than 250. Is that clear? It's very simple, right? Just look at the graph, then it's there's nothing new here, right? And you will see why we want to do this is instead of looking at whether X bar fall into this, I just calculate Z. Is it more than Z alpha? Why? Because I can always, instead of looking at X bar, I look at Z, right? I want to look at this, whether you convert this guy, is it going to fall within this region, right? And so this is the what we call the critical values. Okay, it's the value that you make or break, right? The Z alpha. If you do the one-sided hypothesis testing. Don't worry, I'll give you an example and we'll go over the example. But that is the overarching idea, right? The idea is, let me repeat, you claim equal to something, you reject if too large, right? The question is, how large is large? Okay? And you know the sample means to follow the bell curve, right? The data you got is follow the bell curve. Remember, it's a normal, right? It's a bell curve. And how large is, you would think, if this is right, end up in here and more is very unlikely, right? The alpha is very small, right? Alpha is small, the 5%, right? It's very low probability is true, right? If you fall within this region, then you say, okay, I don't think that is what you said is right. It's too large to be believable, right? Only appear out of 100 times, only 5 times like this. I can't accept this, okay? I will not happy with this. I think it's more than 250. Okay. So as long as your sample means more than this number, right? Remember we know sigma in this case, okay? Based on the n, right? And you can calculate this number. Or this is the one way to do it. Or usually people would calculate the standardized version and see whether this number bigger than the critical value. Okay, the same thing. Either you look at this space or look at this one. Okay? Don't worry, I got the example, and that will be we'll end with the example. So I don't want to overload your mind. Okay. That's for critical value. Okay. Or the other case is, remember what we have is here, right? we will reject this is alpha, right? That's it. This is alpha here. Okay. And the other way is don't look at this, right? The other way around is look at your data. Your data is here, suppose. Okay. You can calculate this area. Okay. If this area is smaller than alpha, you reject, right? Because it's too far away, right? If it is bigger than alpha, you don't reject. That's it. Okay. I think I still have 2 minutes. Then I can go for the example. I still have 2 minutes. Do I? Oh no, I don't. My clock. This one is slower. But the idea you can see. I just don't want to spend one note. But you can see what I do is I have the n, I have the sigma, I have the mean. What I do is I take my sample mean x bar, which is 7, minus 6 is here, over the sigma over root n is 2. Okay. And remember, I calculate 1.64 right hand side. So this is more than this, then you reject. Or calculate area, which is the right hand side area is the p-value, which is 2%, less than 5%. So I reject. Okay. Don't worry, we'll go again this example because this is the procedure we often do for the rest of the class. Okay. We basically do hypothesis testing, estimation all the time for the rest of the semester. Okay. So don't worry about that. We will do it again next class. There's nothing too much left. Okay. So I hope you have good rest for the next week. We don't have class, but do remember after the week after we need to submit assignment. But shouldn't be too much. Okay. If you think it's too much, let me know. The week we come back, we can extend the deadline for the assignment, but otherwise we will keep that. Okay. I see you the week after. Enjoy.